So 4.1 is extreme values of functions on closed intervals. All right, so we got this definition here. Let f be a function with domain D, then f has an absolute maximum. And make sure you pay attention to the wording. We'll have absolute max, absolute mins, relative max, and relative mins. So if it's absolute, it's the absolute maximum value on D at the point C. If notice how this is set up right here, that f of C is greater than all values uh, that are f of x that are in D. So it's greater than all f of x's for all x in your domain, all of your x's in your domain. So you're talking about the largest value, the absolute maximum in your out of your function or on your graph. And then we'll have an absolute minimum in the domain. If notice here at C, when you plug C into your function, it's the smallest value in comparison to all of your f of x's for all your x in the domain. So your absolute minimum is the smallest value that you can get when you plug a value into the function. And your absolute maximum is the largest value that you can get when you plug a value into your function. So maximum and minimum values are called extreme values of the function of f, of the function f. And absolute maxima and minimum are also referred to as global maxima or minimum. All right. I'm gonna make myself enough room. This is not exercise, just something to help further explain the extrema. I see what I probably shouldn't use this terminology over here. Hold on a second. Absolute minimum. Do this 0. All right, so I need that. So we have here looking at y equal to x squared, your parabola. For the first one, your domain is negative infinity to infinity. And I'm going to do a diagram to show you this. I'm just walking through the chart. From negative infinity to infinity, there is no absolute max, just absolute min with the coordinates 0, 0. And I didn't want to use the ordered pairs over here in that right column because I didn't want to confuse them with what we're doing over here at the domain. So if we have the domain going from 0 to 2, then you would have an absolute max at 2, 4, and then minimum at 0, 0. Then if you're talking about open, left side is open, and then right side is closed. In other words, for the interval from 0 to 2, that means there will be no absolute minimum. And then an absolute max at 2. And then if it's just if it's an open interval from 0 to 2, there's no absolute extreme. So let me draw those out so you can see what we mean. So we're looking at A is the first one. So notice what it says here, no absolute maximum from negative infinity to infinity. That's because it's going up to infinity when you look at the direction of the graph, but it has an absolute minimum at 0, 0. So no max because it's continued to go up as far as to infinity, but it does not. But it has a lower value. The lowest value is at 0, 0. All right. So the next one, we're looking at the same parabola, but we're going from 0 to 2. So this point right here, just like we said before, is 0, 0. Just like this point right here is 0, 0. And this point is 2, 4. You know, if you were to plug 2 into the function, 2 squared is 4. Just like if you were to plug 0 into the function, 0 squared is 0. So we have closed circles. So the function does exist. We have the bracket, which represents closed circles. So the function does exist at those 2 points. So we have absolute max at 2, 4, absolute min at 0, 0, the smallest value and the largest value of that part of the parabola. All right, then for C, looking at an open circle down here.
It's open in that one because 0 is not included, correct?
Right, right.
With the parentheses.
You got it. Mm-hmm. And so since that is the case, no absolute minimum, but we do have the max at 2, 4.
So without looking at the graph for C, how would you know that there is no minimum just by looking at the equation?
Well, you would, when you're talking about going from your interval from 0 to 2, and we're going to have tests for this as well. You know, you would plug in values, and if there is no change in sign when you do your plug-in, when you take the derivative, if there's no change in sign, then you know that didn't go lower, or you know there is no max or min. It's like we're going to have tests. Right now, we don't have it because we haven't introduced that yet, but we're going to have tests that's going to let us know whether there is more than just a straight line between 0 and 2. That's going to help us to establish, you know, um, absolute max and absolute mins. Yep, it's a good question, and we'll get there soon. But because there is no neither one of the points exists at these points, there is no max or min. All right, so let's go to the next one. Trying to see which one I want to copy next. All right, so the extreme value theorem, THM theorem for short. If f is continuous on a closed interval, AB, notice the interval is closed using your brackets, then f contains both an absolute maximum value m, capital M, and an absolute minimum value lowercase m in AB, in the closed interval AB. That is, there are numbers x1 and x2 in A and B with f of x1 equal to lowercase m and f of x2 is equal to capital M. And if you look at the notation, lowercase m is going to be the smallest value. Capital M will be the largest value for every other value in comparison to every other value of x in that interval AB. So that just goes back to the diagram that we had on that closed interval. And all the extreme value theorem is saying is that if you have a closed interval, there will be an absolute maximum on that interval and an absolute minimum on that interval. All right. All right, looking for relative extreme values, local maximums and local minimums. I'm going to write local minimum down there in a second, but I didn't want to move past it without talking through it. So a function f has a local maximum value at a point C within its domain D if f of c is less than or equal to, f of x, excuse me, is less than or equal to all f of c, excuse me, for all x that are in D. So epsilon, that just represents x in D, all of your x values that are in the domain lying in some open interval containing C. So basically it's the same definition that we had for the absolute max. It's just that this time, or this can exist on open intervals. So you're just talking about whether it's local maximum or relative max. Both of those are the same. Local max or your relative max. You're talking about the maximum relative to an interval, or like your local maximum, or local like if you had a local store. That's the store that everybody goes to. So that's the maximum for that area. So, and then the minimum is the same thing. Just that we're talking about the smallest value in that open interval. value at point. That's good. So a function has a local minimum value at a point C within the domain D if for all the values of X in D, when you plug it into your function, they are greater than the value you get out when you plug C into the function in that open interval containing C. All right, let me see if I can draw this out real good. All right, I'll do it the way you do it. I didn't do it right. All right, I did the best I could when it comes to that. So let's see. All right, so we got an absolute minimum at A. At C, there's a local maximum, local minimum at E. Yep, local minimum at E, absolute maximum at D, then a local minimum at B. Do this. All right, so characteristics of that absolute minimum at A, there's no smaller value of F anywhere, and it's also could be a local minimum. All right, so the local max at C, no greater value of F nearby. So that local min at E, no smaller value of F nearby. And I don't think I emphasized that this just represents the function f of x. You know, this graph, this line, this wave just represents the function of f of x. And absolute max. And then D, no greater value of f anywhere, also a local max. So we talk about at D. And then at B, that local minimum, that same definition will hold true. No smaller value of f nearby. All right, make sure we're okay before I move off.
I'm good, man. You can move on if you want.
All right, appreciate it. I was checking one thing in the notes before I went to the next thing. All right. All right. So finding extrema, the first derivative theorem for local extreme values. If f has a local max or local minimum value at an interior point C of its domain, and if f prime is defined at C, then f prime of C is going to be equal to 0. All right, an interior point of the domain of a function f where f prime is 0 or undefined is a critical point of f. All right. Okay, so finding the absolute extrema of a continuous function f on a finite closed interval. So we have three steps here. First, we're going to find all critical points of f on the interval. Then we're going to evaluate f at all critical points and endpoints. So your endpoints are, the endpoints of your interval. Then we take the largest and smallest of these values. All right, so let's look at an example. All right, we want to find the absolute max and absolute min. I said mix min, absolute maximum, absolute minimum values of f of x equal to x squared on the closed interval of -2, 1. All right, so first, I want to find the critical value. Because it's just say find. All right. Take the derivative of f of x. Or I could have said find f prime of x, either way. F of x is x squared, so you bring your 2 down to subtract your exponent. Subtract 1 from your exponent, it leaves you with just 1 for your exponent, so that's 2x. All right, so set 2x equal to 0, divide by 2. X is equal to 0. So x equal to 0 is a critical point. I say critical value. You could have said critical point value. But all right, so we found our critical point. We only had one in this case. I think 2 was, let me go back to 2, make sure, evaluate all. Okay, so now we're going to take that, remember f of x is x squared. So we're going to plug in our critical point and our endpoints. I think we had -2, 1. Yep. any problems? All right. So what we can conclude from that is that the function has an absolute maximum value of 4 at x equal to -2. End up being a maximum. And then an absolute minimum value of 0 at x equal to 0. And that was your third step, if I'm not mistaken. Going back to your third step, take the largest and smallest values, right? All right. Questions on the process?
Would the minimum not be 1? Because the endpoint is 4 and 1.
All right, let me go back to the notes. I just switched. Now the minimum goes off of the smallest value that you get after you plug it in. So when we plug in 0, 0 squared gives us 0. So that 0 is lower than the 1. It's like when I plug in -2, I get out 4. So that's going to be my max. All right. Did I answer your question?
Yeah.
Okay. Gotcha. All right. Let's see. Okay. Let's do at least one more, then I'll let you guys go. I'm missing one. All right. that's a good one. All right, I want to find the absolute max and absolute min values of f of x to the 2/3 power on the interval of -2, 3. So first, I want to find a critical point. You need to find a derivative of f of x. So you bring down your 2/3. You subtract 1 from that 2/3. So that'd be 2/3 x to the -1/3 power. Because that 1, of course, is 3/3. And I can bring that down bottom to make it positive. So really that is the cube. That's 2/3 cube x. All right, so here, let me see, I can write this. All right, so there's a critical point at x equal to 0. F prime is not equal to 0 at x equal to 0, but it is undefined there. So if I were to put 0 in the denominator, if I were to put 0 in the denominator here, that gives me 0 in my denominator. So that would be a critical point. All right. All right, so second one, we go ahead and plug those values in. So we have a critical point at x equal to 0. And our function was, I lost that's our original function. So we plug that in. Of course, 0 to 2/3 power is 0. Now plugging in our endpoints. Don't forget, when it comes to your exponent being fractions. The top number, your numerator, is your power. Bottom number is your radical, or the index of your radical. So we're talking about -2 squared, or the cube root of -2 squared, then the cube root of 3 squared. So we're looking at the cube root of 4, cube root of 9, these are your endpoints. Is it, oh, my words right. Hold on 1 second. Yeah, the word is right. Absolute max of cube root 9 at x equal to 3. Absolute minimum of 0 at x equals 0. All right. Questions with the process. All right. Also, when you check your critical points, make sure it is in the interior of your interval. So if I had a critical point of 0, but let's say that this interval went from +2 to 3, then that critical point wouldn't matter because it's not in the interval that we have. But since it's going from -2 to 3, 0 is in between -2 and 3. So it is an interior point of this interval. All right. Questions, concerns, comments on anything? Well, all right. That is 4.1. So as always, try the stuff out. See if you get stuck. See if you have any concerns or comments, or concerns or issues, and we will hash it out on next class. Other than that, you guys have a good one, and I will see you on Wednesday.